But anyway, we're back in business. And before we get started on the matter at hand, which would be more on the golden ratio. By the way, it's going to get a little more mathematical today, in a good way, I hope. I wanted to talk about the rest of the semester, what we have left. And one of the reasons why I didn't want to announce a schedule earlier is because I may have to take a day off, but I'm just not sure which day. So I think it's probably going to be Thursday next week, and so that might put a little wrench in my plans, or in our plans. But we should be definitely still doing stuff next Tuesday. I'm going to assign a project today. Will be due next Tuesday. And then we have, so let's assume for the moment that I have to take next Thursday off. So then that would basically leave us with May 4th, 6th, 11th, and 13th. So April 27th, May 4th, May 6th, May 11th, May 13th. Now there's plenty of time to do, I want to talk about at least fractals with you guys for a couple of days, and then we're going to do some review, and then we're going to have the second exam. Now here's the thing though. I kind of know how the vote's going to go. I want to do a vote. We don't have to do it right now, but I want to do a vote maybe later today or next time. But the issue that I've been struggling with is whether to hold like a more traditional final exam where we cover everything that we've talked about, or do more like a exam 2 where we just cover the stuff that we've done since the first exam. Just a big Kahoot battle. We could definitely use Kahoot to practice. So I'll let you guys think about that for a little while. I mean, obviously, if we just had an exam 2, starting with the wallpaper patterns, it would be less to study. However, don't forget that what some might consider the hardest topic, which is the wallpaper patterns, would take on a little bit more significance. Fiona, what's your comment?
So I looked at the Blackboard today, and it said that the thing was due today, but it also said that it was due the 27th. The homework. I know it's like off topic a little bit, but
let me see. I may have been editing things right at that moment. There's nothing due today as far as.
Okay, so yeah, it's because on it says due 4/22, and then it says due 4/27.
Oh, that's my accident. Yeah, yes. That's just I must have just looked at the calendar and just put today's date. Okay, I just fixed it.
Okay, perfect.
If you look at it now, you'll see the right date. Yes?
Hi, sorry, I meant to tell you, about like an hour ago, Ria in our class texted me that she was having internet problems and that I think her phone was about to die, so she can't even join. There was like a power outage.
There's been a death in the household. Okay, well.
So she said that she would email you once her power came back on.
Okay, or you could just tell her that just watch the recording. Ria, we're with you. You're with us in spirit. Hang in there with that.
I'll let her know.
That dying internet connection and the phone. Oh my gosh. Hopefully no personal injuries. Only a Wi-Fi connection and phone. All right. Anyway, so any other questions before we take a plunge into a more mathematical side of the golden ratio. We're just going to basically pick it up where we left off, but look at less pictures maybe today and just talk a little more math. And we're going to focus on the relationship between the long side and the short side. And in golden things, that relationship is pretty much set. But there's this additional little thing that I didn't even mention last time, because I need to draw some diagrams and kind of I wanted to keep last lecture as kind of a visual teaser, if you will, like the hype session. Although I'm kind of the anti-hype guy when it comes to the golden designs, because I think it's overhyped a little bit. This is not the last lecture, no. We're gonna have one more topic, the fractals, which is very fun and different. And we'll probably do that next Tuesday. My guess is that I'm going to have to take off next Thursday, but I'll let you know as soon as I know. And hopefully there'll be no confusion about that. I'm guessing at this point we could have the final either on the 11th or the 13th. It kind of depends how much review you guys want. When I say the final, it might end up being more like an exam 2. So May 11th or May 13th, that's the last week. So we just have to have the test on that last week. If you guys want to, we could say 11th for now, May 11th, and then just kind of see how things go. All right. We can even vote on that. We could see how what people feel. So the golden ratio. Let's roll up our sleeves and get to work. So this is the second lesson on the golden ratio, and it's sorry, my writing looks like Bart Simpson's, but it's just the way it is right now. Whoops. I will not write like Bart Simpson. I will not write like. All right. So golden ratio. So something to how I was talking about the Fibonacci numbers last time? That was one approach that you could take to arrive at the special ratio. I'm going to now offer another approach, and it's going to help us just kind of solidify things, and it'll also show how seemingly unrelated things are actually connected through this special ratio. You will not have to reproduce this argument or this construction. So I'm not going to ask you to prove anything or anything like that. It's just that, in my math teacher's conscience, I can't leave this topic without telling you guys a little bit about this certain. Oh, let me. I guess I'm just going to have to trash the whole thing. I forgot that I have a line tool. This is a fancy program. I got a line tool. So what I'm going to talk about now is a special way to cut a line. To divide a length, a measurement, into two in an interesting way. Now, what is that interesting way, you say? One thing I could do is just cut it right down the middle. A lot of times we do that. You know, let's say you're taking a photograph and you're wondering, where should I put my subject? Where should I put that interesting thing that I want people to focus on? A lot of times we put it right in the middle. And that might be appropriate for, let's say, a portrait, you know, a headshot, something like that. But there may be a better way to place something if you're doing something else. And so this special way to cut this distance into two has a special property. So I'm going to cut it right here. And what's special about it is that, let's call this, I'm going to use some symbols here. Again, you will not have to reproduce my argument, but this is something that I feel like I must do. So we can call it the whole line segment, we'll call it L. I'm going to call this part that, you know, is a little longer than the other part. I'm going to call it M for, I guess, medium length, and S for short. So you could think of it as long, medium, short. But L could also, you know, be for the line. Okay, so the special property that I want this cut to have goes like this. I want the ratio of the whole thing to that M piece to be the same exact ratio than the two pieces M and S. This is something we did not talk about last time. So I want to cut this distance so L over M, the ratio of L to M, is the same as M over S. And to figure out what that might be, and by the way, there's a way that we can figure this out. And at the face of it, you might be like, he is not giving us enough information. I mean, what is this length to begin with? Well, luckily that doesn't matter. This works for any length line segment. Okay, could be a mile long, could be an inch long, it doesn't matter. Still, you might feel like, oh my gosh, there's just not enough info. Well, let's see. Let's call this common ratio X. So let's see, X. It's just weird, right? It's like, how do you even approach this thing? It's just a bunch of letters. But there's something that I haven't told you, or it's there in the picture, but maybe you didn't think of it. I'm going to use the fact that L is sum of M and S. So this X thing, remember it's L over M. I could write this as M plus S over M. Now, M plus S over M, I could break that up because I have a sum in the denominator, in the numerator, and just one thing in the denominator. So I could write it like this. And the nice thing about this, it looks like a 5. That's supposed to be S. The nice thing about this is that I can actually write the m over m. What's m over m? Can somebody tell me? There's a real easy way to write that.
Is it 1?
Let me just cancel
Yeah.
out.
M.
Yeah, so the m's kind of cancel out and as the common factor for both top and bottom, and what you're left with is 1. Now, then I have this S over M thing. Can anybody tell me what I could do with that S over M? And let me just repeat, you do not have to know what I'm telling you for the second exam. Okay, I'm not going to quiz you on this, but I just feel like I need to show it to you because, well, it's great stuff. So does anybody know a different way to write S over M? Something that would be useful for us here. S over M. There's something that's very close to that here. See, X is M over S.
So there's would still be no, it wouldn't be X.
X is in there, but it's not the same as X. It's flipped, right? What's the name for flipping a term? Anybody remember?
Mirroring?
Reciprocal or something?
Reciprocal.
Oh, yeah.
Yes. Yeah. We have here is now the statement that we have in terms of this ratio, X. So X is to 1 plus 1 over X. 1 plus reciprocal. So what? Well, check this out. I'm going to multiply both sides of this equation. That 1 over X thing. You probably don't like it either. So I have here then on the left side X times, which is X squared, 1 times X. Basically what I'm doing now here is this, right? And 1 times X is X. 1 over X times X turns out to just 1. The X's cancel out. Can you hear me okay? Not sure if you can hear.
I think your audio might be cutting out a little bit.
Yeah, just a little.
Yeah, I already turned off my camera. But all right, so let me put it all in one side like this. Does this lead to any? Hold on, I'm gonna or so maybe I'll get better reception. 1 second. Does this look familiar to anybody? This might bring back some memories from high school. This is what's called a anybody? Quadratic equation. That means it's got a second power, right? It's an equation with one variable and a second power. So, and maybe you remember how to solve it. Does anybody remember?
Okay, quadratic formula. I'm trying to see if I remember this. Is that the thing that's
Yes.
it's oh my goodness. I remember I had to sing a song. Is it the 2, right? It is 2. No, I'm completely wrong. It's negative b plus
Yeah.
and minus.
It's in there somewhere. Yeah.
Um,
There's a song.
yeah, I'm trying to remember the song. The square root of b squared, I think.
Yeah.
And then
It's in there. Back.
minus, and then I forget, yeah, and then I remember it's all over 2a.
Taylor. Thank you, Taylor. Yeah, that's it.
All
Anybody
I
want to sing
remember is
it?
the end of the song of over 2a.
I haven't been in high
Anybody want
school
to
in
sing
like
it?
4 years, so this is all like coming back to me now, and I'm like, oh my God,
Same.
quadratic formula.
Yes.
I
Yes.
don't really
Yes.
remember any math before like sophomore year or after sophomore year.
Okay, you don't
Same.
have to know this formula. It's just we're just reminiscing the old algebra days, and I'm gonna try to make it quick so you got like you're learning something that you shouldn't be, because it's not on. Okay, but I'm just telling you, I feel like I gotta put it in because this is a great approach, another approach into the golden ratio. And you know what? I shouldn't apologize. I'm not going to apologize. This is a perfectly wonderful thing to do. All right. So in this quadratic equation, we have the A, B, and C terms, right? They're the coefficient of the various things. So the x squared term, whatever the x squared term is, the coefficient is the A. The x coefficient is the B. Constant term is, and I already wrote it down here. A is 1, B is -1. Let's plug these in. -1 plus minus, and then we're going to do the square of, and then 4 times, just plugging in A, B, and C. This is stuff that you did in high school, I'm sure, lots of times, and I'm sure some of you may not have liked it, but on the test. So just if you don't want to watch, just watch or something for the next 3 minutes. All right, so negative is 1 plus or minus, and inside this square root I have -1 squared, which is 1, and then I have -4 times 1 times -1. Now that's 4 because of the two negative signs. 1 is 2. All right. 1 5 over 2. Now, if we were to evaluate this thing, so by the way, found x, we just found that special way of cutting a line so that the whole thing divided the longer piece is the same ratio as the longer piece divided by the shorter piece. So we just figured it out. Now, if you were to evaluate, you'll notice that using the negative sign will get you a negative number. So I'm going to go ahead and do the old math teacher trick that we can ignore this negative because it's not giving us any helpful information. A lot of times, most of these quadratic equations have two, and so does this one, but the other root is a negative number, and a negative ratio doesn't make a lot of sense for us right now. So x equals 1 plus square root of 5 divided by 2. Now, someone with a calculator, could you evaluate this? You could do a square root of 5. I have my phone here, and I can, if I turn it this landscape, I can do square root of 5. And plus 1 equals, and then divided by 2. I have to run off a little bit. Get an answer? Is it just me geeking out on this stuff? Well, maybe not surprisingly. 1.6 0 9. I'll just put another 9 here. That's phi. This is phi. And so this is another way to look at phi as a mathematical property or a number of interest. So it's got this special property that the whole thing divided by the larger piece is the same ratio as the larger piece divided by the smaller piece. And that's going to come in handy when we work out some problems. Is it helpful? Is it good to know? Maybe just as a way to deepen your understanding of the golden ratio. I mean, ultimately, let's say and you want to do something interesting with it. Are you going to start using the quadratic formula when you're taking a photograph? Why I did it. You're gonna take your picture, maybe thinking, oh yeah, let me put it slightly off center. Sometimes people use what's called the rule of thirds, and that's kind of close to what we're doing here. This is not quite that, but it's a similar type of it's the same kind of idea that you want to place something right in the middle. So where should you place it? You can just kind of go third off the side, or if you want to get a little fancier, you can use the golden ratio. Just a kind of a starting point, just a habit thing that you can use to make your visuals more appealing. Now, this in-depth knowledge that I'm just giving you now, yeah, just to deepen your understanding. Okay, I want to do some. I'm sure everybody's shocked now, like, oh my God, look at this crazy ratio. It's got all these properties. Honestly, we haven't even cracked the surface. These couple of connections that I mentioned, the Fibonacci numbers, how phi is the what's called a limit in mathematics. So successive ratios of adjacent Fibonacci numbers approach this number phi. We talked about that on Tuesday. So connection, and then this this connection mentioned. These are just little bits. Turns out that there's just a ton of stuff in mathematics that ends up connecting to phi. And it's really cool to know about. So if you want to know more about the math side of it, then I recommend you look up this book. By an artist named Mario Livio. And I'll show you the cover right now since while we're at it. I see that it cost $3.99. Oh, here's a version of it for, oh yeah, $3.99. I'll share this with you. So it's definitely affordable if you're into learning. This is the best book that I've come across, from the math perspective. But it's totally like the kind of pop math. It's totally readable. There's not a ton of formulas or anything like that. It's really it's just full of these curious mathematical oddities that all end up connecting to phi. And so if you're into these kind of little math mysteries and that sort of thing, you should look into this. Notice the pentagons here in the cover. By the way, I hope you noticed the number 5 showing up in that calculation. You notice that? We ended up with an exact form. Oh, now that we know that it's phi, I'm going to do an exact. So this is no approximation, okay? So phi is equal to. So I just derived this using a little bit of geometry. Phi is equal to. This is like, even though it's an irrational number, we can find something that it's actually equal to. And yeah, I recommend you put this in your calculator and see for yourself. But notice that 5 in there. There's that 5 again. The pentagon and the pentagram have a lot to do with the golden ratio. So it's pretty neat to see it in that exact formula. But as we saw the other day, there's also many other things. Like for instance, it's this continued fraction. If you did this, and I'll just put dot, dot, dot. You just keep doing this, and you will end up with a very good approximation of phi. The further down, the more ones you have in your fraction approximation you're going to get to phi. It's pretty mind-blowing stuff, to me anyway. Okay, so what are we going to do now? I would like to share with you some problems. I've already posted these on Blackboard. And I want to talk about these now. And whatever you don't get to yourself, you can do this as homework. But my goal would be to actually do all 6 problems here during class. And I also posted the answers to all of these on Blackboard on our week 12 Thursday page on Blackboard. Now this is the kind of stuff that will show up on the test. So I'm going to guarantee right now that something like this will be on that second test. So number 1, the line segment below is divided into the golden cut. Find x. All right. This seems an awful lot like my construction. This sounds like, oh yeah, I just cut a line segment in this special way. So I know that the ratio of 5 over x, so what do I know? I know that ratio of 5 over x is the golden ratio. Ratio of 5 over x is the golden ratio. I'm cutting out again. Hold on, let me go open my door again. I have to keep the door open because my Wi-Fi is very weak. Okay. Okay, let's hope that that's better. Yeah. Okay, so 5 over x is so this is problem number 1. 5 over x is the golden ratio. Now, do this once the long way, and then I'm going to teach you a shortcut. How's that?
Sounds perfect.
I want to teach you the long way so that you know where the shortcut comes from. But basically, there's no reason for you to do long calculations when it comes to phi. The reason for that is the ratio is always the same, right? So the question is, am I looking for a number that's bigger, or am I looking for a number that's smaller? And I'm going to do this very same problem 2 different ways. The first, I'm going to do the long way. So the ratio of 5 over x is golden, so that's phi, and I wrote it over 1 because I want to show you how I would cross multiply. So this is a little bit of algebra that you don't actually have to do if you follow my shortcut in just a minute. So that means phi times x equals 5 times 1. If you're freaked out, then just wait for the shortcut, okay? The golden ratio is a number. It's not a variable. The only variable here is x. X is the unknown. And so phi is a number. And you could write it as 1.618. But for now, I'm writing it as phi because it's just a simple single symbol. I'm going to write divided by phi on both sides. Like so. So it's going to cancel on the left side. And so on the right side, we have 5 divided by phi. And now I'm going to, for the evaluation of it, I'm going to approximate. This little wavy equal sign means approximation. 1.6. And when I plug that into my calculator, 5 divided by 1.618, I get a smaller number. I put in there, you should round to the, comes out to be 3.1. So if you have a line and you're told that the cut is so-called golden, then if this is 5, side is 3.1. And what I just showed you is the kind of the algebraic way, the long way of doing it. Now let me explain the short way. Typically, we're dealing with 2 lengths or 3 lengths. And I'll just put 1 length here, next length here, and this length here. The long one, this top one, is actually the sum of the bottom 2. Now, in this case, the 5 is this middle number. And we were asking about the shorter number, or we were being asked about the shorter number. So if you want to go shorter, you're going to divide by phi. If you want to go longer, you're going to multiply by phi. And that's all there is to it. This is 5. The top one is then times 0.61. The bottom one, the shorter one, is 5 divided by 0.618. So that's my shortcut. You don't have to do any crazy algebra, cross multiplying, or anything like that. You're always either multiplying by phi or dividing by phi. So if you want a bigger number, you multiply. If you want a shorter number, or a lower value, you divide. And phi is a number that's greater than 1, right? So ratio is always the same. It's been the same since nobody came up with it. Some people call it the ratio because like to connect it to something that a divine entity created. It's always been there, and it's always been this connecting all these weird, seemingly coincidental math properties and objects. But in any case, it's a constant. So if you're looking for a shorter piece, you divide. If you're looking for a longer piece, you multiply. That's my shortcut. Okay. Keep in mind, I bet we could do this. So let me put up the problem set once again. And here, number 2, the line segment below is divided into the golden cut. Find x. That the whole thing, the whole line segment is 10. How can I find x? Anybody want to take a stab at it?
Can we do another example? I'm still kind of confused on it.
Okay, so I'm going to work this one out then on my board here. So
don't you multiply by phi 10?
If I multiply 10 by phi, I'm going to get 16. Could x be 16? X is a smaller number than 10, right? So yeah, Nicolette, you got it right. 10 is going to be divided by phi. That's all there's to it. But I'll show you again. So if the whole thing is 10, and I'm looking for x. If you think about my three lengths, the L, M, and S, the 10 is the L, and the middle one. So I want a number is shorter than 10, less than 10. So I'm going to divide by 1.61. And I know I put an equal sign there. It's really approximation. And we'll round to one decimal. Yeah, 10 divided by phi, 10 divided by phi. And you actually get an interesting thing happening here. Because phi is, I should do, I said I was going to approximate to one decimal, so 6.2. If you divide 1 by phi, you get phi minus 1. That actually comes from how we had the, from that equation that we set up with the L, M, and S. If you square phi, you get phi plus 1. These are just weird properties. If you cube phi, that's also related. Okay, so anyway, so if x is 6.2, then now just for kicks, how would you get the short piece then? How would you get this? Say if I was looking for both. Right, so you could divide 6.2 by 1.618. Another person might say, oh, well, can you just subtract 10 minus 6.2? Yes, you can. That's another way of doing it. Okay, number 3. Find x so that the rectangle is a golden rectangle. So I'll put this on my white screen. So I have 7 for height, and that's the short side, and x is the long side. So if you're given that the rectangle is golden, I'll even type it in here. This is a golden rectangle. Any rectangle. As soon as you say that the rectangle is golden, you're locked in. You know, you're locked into this relationship with the long side versus short side. The relationship is that the ratio between the two is 1.618. Now, there was a question, how would you get the answer by dividing 6.2 by phi? Well, I think you answered your own question. 6.2 divided by 1.618. Now, let me ask you guys, is x a bigger number than 7 or a smaller number than 7? Bigger. Now, how do we get the bigger number? We're gonna. There's only two things to do. Yeah, you either multiply or divide. That's right. So I'm using my own shortcut now. So 7 multiplied by phi, get 11.3. So if I had a golden rectangle with the short side being 7, the long side is going to be 11.3. Notice that I'm not going to say height and width because what if your golden rectangle was like this? It could be portrait and still be golden. That's why I like to talk about long side and short side. Here the short side is the width, and the long side would then be the height. So it's not always true that the rectangle is, portrait or landscape. It could be either. Why do we multiply 7 by phi? Because we're looking for the next length. Remember, we have sort of 3 lengths. We have. I'm going to draw with the with my red here. This here is the short side. I'm going to draw 2 lines, 2 red lines here. Here's my middle length. The large length, you could think of it as the height and width put together. The length of that is the whole thing. Now, why would I even say that? Why complicate matters now? Well, look at the next problem. By the way, I'm just saying the same thing over and over again. You've got 3 lengths. You got the whole line segment, and then you got the medium piece, should do x, or the what's the 7, and then the long piece, the 2 together, that would be the L. If we look at our next question, you can kind of see why I set it up like this. If the perimeter of a golden rectangle is 24, find the height and width of the rectangle. If the perimeter, and you know what a perimeter is, right? It's the length of the fencing around the rectangle. Or if you had, you could think of it as you have 24 inches or meters or whatever. You have the length of a rope is 24, and you want to make a golden rectangle out of it. The biggest possible golden rectangle you can. So what we know here is that the perimeter is 24. And once again, we are dealing with a golden rectangle. How long are the height and width? What are the dimensions? So I'll take suggestions. Anybody has any bright ideas? Any ideas? I'm looking at a hole whose perimeter is 24. How long are the height and width? That is simple to state. Mateos coming through. Oh my goodness. So what did you do? What's can you explain to your friends here?
Well, if the whole perimeter is 24 and we just want two sides, that will be half of 24. And so then we divide that by phi, right?
This and this is 24, right? Because that's only half. So yeah. So now what was 24 divided out of that? 24 by 2 was what?
12.
12. Okay. So if we draw this diagram here, now I'm going to do a little something. I'm going to do a little visual. Okay. It's as if I should maybe do it on the other side. I'm going to pull down this line here. And I'm going to think of it as a combined line segment like that, where the corner is cut like, about here. So what you're telling me is that the width and height together is 12. Texted in the chat was if you divide 12 by that magic number phi, you will get the long side. Right? Now, what did you get when you did that? $7.4. Excellent. So if we're just going with 1/10, so the long side, the way I drew it, that would be the width. Long side is 7.4. So what would be the short side? Aiden was asking, well, how the missing side then? We just give him one dimension, say, oh, we can't figure out the rest, but the long side, oh, there we go. There we go. Man, this is starting to make sense to some people. So we have what we have left. Yep. So I'm just going to write this long side 7.4. Short side Bada bing, bada boom. So that's why I've been talking about the whole thing put together, the long side. I mean, the sum of the long side and the short side. Because without that concept, we couldn't really do this. All right. Ooh, wow. I can tell you this. That was the hard question. Okay, so the remaining two are a little easier. Let's see what we have. Number 5. Suppose this triangle is golden. Find x. Now notice here, we haven't talked a lot about golden triangles, but the same thing applies. The long side divided by the short side is phi. So you can do the calculation with the cross multiplication and all that, or you can just say, oh, I know the short side, I'm looking for the longer side, I'm just going to multiply by phi. So it'd be 4 times 1.618. And number 6, is this a golden rectangle and why? So I'm going to work that one. So phi and phi squared. So let's see. Phi is phi squared are the dimensions. Remember, phi is not a variable. Phi is a constant, 1.618. You could find your numerical values for these number values. It is weird though when you put in the calculator and you find out, oh, phi squared is actually just it's weird. It's 2.618. It's the one number that has this weird property that to square it is the same as adding 1. So I don't need to know these 1.618 and 2.618. All I need to know is, or ask, is the ratio phi? Because if the ratio is phi, then it's golden. And of course, squaring a number is just the same as multiplying it by itself. And I can do this little tidbit. Look. And I can cancel 2 of those like that and end up with phi. So yeah, the ratio is phi indeed. So yeah, check. That's a golden rectangle. As long as the ratio between the long side and the short side is phi, yeah, it's crazy. I don't know if I can sleep tonight. Oh wait, I already knew this. Maybe you can't sleep tonight. There's a lot. If you're really actually interested, then you order that Mario Livia book for $4, and it'll be one of the best ways you could spend $4. I can guarantee you that. Not going to say the best possible way, but there are good ways to spend $4, and that's one of them. Okay, so I did want to mention something about the project. It's already posted online on Blackboard. Golden Project, it's due next Tuesday. You are to create an original design, whether that's a logo for some imaginary company or maybe your own company, or it could just be an abstract thing, or it could be whatever you want. It's really wide open. All you have to do is utilize the golden ratio, some form or another. it could have that golden spiral thing going on. It could have a golden rectangle. It could have a pentagram. It could have a golden rectangle, golden oval. However you want to put it in there. As long as it's in there somehow. I mean, people find ways, and I mean, are they all good? I don't know, but like this textbook of ours, for instance. You remember the textbook? Oh, I can't do my video. Anyway, the textbook has a golden ratio in the cover with the two colors. It's a two-toned background there, and it's like a brown and green thing. They are in the golden relationship. So yeah, the golden spiral, you have to kind of construct it using those Fibonacci numbers. That's one way to do it. Not every spiral is a golden spiral. If you look up golden spiral online, you get all different kinds of spirals. It's crazy how like misconstrued and misunderstood the whole thing is. People will look at some staircase and say, oh, that's the golden spiral. Most of the time it's not. It'd be really difficult to make a golden spiral staircase, actually, because it does wind out kind of quickly. But anyway, you can utilize it in any which way you like, as long as it's there, and you can just submit that to Blackboard by class time on Tuesday. All right, that is all I got. Just look for those golden relationships. Maybe you already have a golden relationship with someone. Oh wait, no, that's different. This probably doesn't apply to human relationships. This could apply to music, for instance. And in fact, there have been film directors that have used it in their edits. Like they'll make scene lengths have a golden ratio, like adjacent scene lengths. And musically, you could count notes and things like that, timing wise. People have made all kinds of compositions doing golden relationships. In fact, if I had more time, I'd show you this little music piece where the composer decides to make a deliberately golden piece of music, and I'll send it to you. It's interesting. It doesn't necessarily sound that great, but it could always be. I mean, he's really good though. He makes the best of it. But it's always a thing to start with something. You can even break that rule. Like if you're working on a project and you start with the golden ratio and the project's kind of going in different direction. Well, okay, there you go. But at least you got it started and you got it rolling, and then you can make it whatever you want. No one's gonna pay you less money for it because it's not exactly the golden ratio. Who cares? But it could always be a starting point if you're struggling to get started. Alrighty, let's go eat, and I hope you have a great weekend. I will keep you posted on the schedule for the remainder of the semester. Okay, bye.
Bye, Professor. Thank you.
Thank you.
Yeah.